Welcome to this explainer. Today we're going to completely demystify the incredible physics behind magnetic resonance imaging, or MRI. We're going to look at exactly how we take invisible microscopic quantum behaviors and translate them into the literal life-saving medical technology that hospitals all over the world rely on every single day. It's a seriously fascinating story of physics, engineering, and human biology. Let's get into it.
Here's our roadmap for this explainer. We're covering 1. The power of magnets. 2. Your body's tiny magnets. 3. The physics of resonance. 4. Medical marvels. 5. The pioneers of MRI. And finally, 6. Limitations and risks. All right, starting with Section 1, the power of magnets, a force to be reckoned with. We're starting our journey by looking at the raw, invisible, and honestly sometimes dangerous power that makes an MRI even possible in the first place. Consider a standard hospital wheelchair violently ripped right across a room by a 3.0 Tesla magnet. When we say these machines are powerful, we literally mean it. In this specific incident, that wheelchair was flying at around 30 miles per hour before it smashed into the scanner. Fortunately, nobody was hurt, but it perfectly highlights the sheer physical force we're dealing with.
And man, this mistake was not cheap. You see, the magnetic field in these superconducting magnets is essentially never switched off. Because of that, the hospital faced a massive bill. It cost a whopping £20,000 just to safely power the system down, pry the wheelchair off the machine, power it back up, and fix the crushed plastic covers.
To put that terrifying power into perspective, let's look at this number. The 3.0 Tesla magnet inside a standard clinical scanner is a mind-boggling 50,000 times stronger than the Earth's own magnetic field. Yeah, the exact same field that compasses rely on to point north, which sits at just 60 microtesla. 50,000 times stronger.
This comparison really perfectly illustrates the scale of what we're talking about. Your everyday fridge magnets, they're about 50 times stronger than the Earth. A massive electromagnet used to lift heavy, crushed cars in a junkyard, that's about half a Tesla, or 10,000 times the Earth's field. But the clinical medical device you casually lay inside at the hospital, that is up to 3.0 Tesla. It absolutely dwarfs industrial lifting magnets. It's wild.
Moving on to Section 2, your body's tiny magnets, the canvas of hydrogen.
So if an MRI is basically just a gigantic, super-powered magnet, how on earth does it actually take pictures of our insides? I mean, magnets attract metal, right? Not flesh and bone? Well, the secret lies right inside our own biology. The crucial point here is that humans are incredibly wet creatures. A typical adult is made mostly of water, around 60%, and another 16% fat. And what do water and fat have in common? They are absolutely packed with hydrogen atoms. This massive abundance of hydrogen is the ultimate canvas that the MRI machine uses to paint a picture.
Now here is where the quantum physics kicks in. The nucleus of a hydrogen atom is just a single proton. Because it has a quantum mechanical property called spin, along with an electrical charge, we can actually think of every single hydrogen proton in your body as a microscopic bar magnet. Normally, they're just pointing in totally random directions, but the second you slide into that MRI tube, those billions of tiny biological magnets are forced to snap into alignment with the scanner's massive magnetic field.
The exact way they interact with that field is governed by a fundamental constant called the gyromagnetic ratio. You can think of this ratio as the mathematical bridge that dictates exactly how much torque these tiny biological magnets experience when they're hit with the scanner's immense power. And because every distinct type of atomic nucleus has its own unique gyromagnetic ratio, we can use it to specifically target just the hydrogen.
Which brings us to Section 3, the physics of resonance, making the magnets dance.
Okay, so now that our body's protons are lined up with the MRI's magnetic field, what's next? How do these billions of tiny aligned body magnets actually create a medical image? Because just pointing them all in the same direction isn't enough to give us a picture. If they just sit there, we learn absolutely nothing. To get usable data, we have to disturb them, push them out of alignment, and then very carefully measure how they recover and relax back to their original state.
Think of these tiny protons like a spinning toy top or gyroscope. If you tip a spinning top, gravity tries to pull it down, but the spin causes it to wobble in a circle instead. This wobbling is a phenomenon called precession. In our bodies, the MRI's magnetic field acts exactly like gravity does on that top, causing the hydrogen protons to wobble in a very specific, perfectly measurable circle.
The exact speed of that wobble is called the precessional or Larmor frequency. In a 3.0 Tesla scanner, these protons wobble at exactly 128 megahertz. Now, why is that number so amazing?
Well, because 128 MHz sits perfectly in the radio frequency range. That means to disturb these protons, we don't need dangerous rays, we just use simple radio waves. This is exactly why MRI is incredibly safe. It entirely avoids the dangerous cancer-causing ionizing radiation you'd get from an X-ray or a CT scan. So after we blast them with a radio pulse, we immediately turn the radio waves off. As these protons relax and their wobble decays back to normal, they act like tiny moving electrical charges. And as they move, they induce this really weak decaying voltage into the MRI's receiver coils. This is a phenomenon known as free induction decay. And that fleeting, tiny electrical whisper caught by the coils, that is the literal raw data that the computer uses to draw the final medical image.
All right, Section 4, Medical Marvels, Seeing the Invisible.
By mathematically decoding those tiny electrical whispers, we basically go from abstract quantum physics to actually saving human lives. The breathtaking soft tissue contrast it provides is just incredible. Unlike X-rays, which are, great at showing dense solid bone, but terrible at showing squishy stuff, MRI absolutely excels at the squishy stuff. By tweaking exactly how we measure that proton relaxation, an MRI can distinctively map out muscles, fat, ligaments, and delicate internal organs in virtually any geometric plane, axial, coronal, or sagittal. It gives doctors a flawless 3D map of the inside of a living person. This unparalleled contrast makes MRI pretty much the ultimate diagnostic tool across almost every medical discipline imaginable. Neurologists use it to spot strokes or multiple sclerosis plaques in the brain. Oncologists rely on it to find the exact microscopic boundaries of a tumor. Orthopedic surgeons use it to see a torn ligament in a knee. It literally allows doctors to see the invisible without ever having to make a single surgical incision. It's a total game changer.
Let's look at how we got here in Section 5, The Pioneers of MRI, A History of Brilliance.
Mapping out the water in our bodies wasn't some overnight discovery. It took over a century of brilliant minds and Nobel Prize-winning physics to pull this off, bridging multiple scientific disciplines along the way. This timeline beautifully traces the evolution of this life-saving tool. It starts way back in 1896 with Peter Zeeman observing the quantum splitting of spectral lines. Then we jump forward to 1952 with Purcell and Bloch winning the Nobel for discovering nuclear magnetic resonance. And finally, in the 1970s, scientists like Damadian, Lauterbur, and Mansfield figured out how to use magnetic gradients to turn those resonance signals into actual spatial images, culminating in another Nobel Prize in 2003.
And here's a fun fact to kind of humanize all this high-level physics. It's reported that Paul Lauterbur, one of those 2003 Nobel laureates, was actually inspired to use magnetic field gradients, literally the breakthrough that allowed us to build 3D medical images out of raw magnetic resonance. Well, he was simply eating a fast food hamburger. It just goes to show you never know when or where scientific inspiration is going to strike.
Finally, we arrive at Section 6, Limitations and Safety Risks, the Trade-offs.
As miraculous as this technology is, no medical tool is completely perfect, and MRI definitely has some very real trade-offs. Because the whole process relies on measuring the relatively slow relaxation of protons, MRI scans take a long time, sometimes up to an hour, especially compared to a split-second CT scan. It's incredibly loud due to the magnetic gradients physically vibrating, it can't directly visualize calcium in bones very well, and perhaps most famously, sliding a patient into a tight 60 to 70 centimeter tube can induce some severe claustrophobia. Plus, the machines themselves are just incredibly expensive to run and require highly trained radiographers to operate them safely. But honestly, despite those limitations, the physics of MRI remains one of humanity's absolute greatest achievements. It really makes you wonder, if mastering something as microscopic and abstract as the wobble of a single hydrogen proton revolutionized modern medicine, what other secrets of physics are just waiting to be discovered to save lives tomorrow? Thank you so much for joining me on this explainer, and keep questioning